Hello everyone, thanks for joining this presentation. So today I'm going to talk a little bit about Android and how the Android open source project differs from other Linux distributions or embedded Linux distributions. So my name is Sergio Prado. I've been working with embedded software for a lot of time. Currently, I've been working with Toradex. I'm the team lead of a project called Horizon. That's an embedded Linux platform based on containers. I have also my company. I've been doing a lot of consulting and training in the last years. I've been contributing to some open source projects also, like the Linux kernel, build root, and the Octo, and sometimes I write some technical stuff at my blog at embeddedbits.org. So let's go directly to our topic here. I would say we have here four main objectives that I would like to cover in this presentation. So our idea here is to compare Android with another Linux distributions. Since we are in an embedded Linux conference, so we're gonna compare what it's like to work with an Android on an embedded device and what it's like to work on an embedded on an embedded device with Linux, with a pure Linux system. So we're gonna cover from the user perspective. So you are a user. What's the difference between working with an embedded Android and an embedded Linux system? You are an application developer. What's the difference between writing applications for an embedded Linux device and for an embedded Android device? And also from a distribution maintainer perspective. So you will port or create a distribution for an embedded device. What is the difference between creating this distribution for an embedded Linux system and for an embedded Android system? So we're going to try to cover these three perspectives from the user, application developer, and the distribution perspective. And of course, to cover all of that, we need to understand the architecture of an embedded Android system. So we're going to talk a lot about the architecture, and then we're going to compare with an embedded Linux system. If we think about what is an embedded Linux system or what is a Linux system in general, right? We have mainly three components. We have the bootloader that will basically boot the system. So it's going to be started by the hardware and it's going to load the kernel, possibly a hand disk, device trees, and start up the kernel. Usually after the kernel starts, the bootloader doesn't do nothing and doesn't even stay in memory. And then the kernel boots, and then the kernel will do all of the initialization and then mount a root file system and call the init process. So the bootloader has the only objective to boot the system. The kernel has the objective which should manage the operating system. And of course, you give some meaning to the system in the user space, where we have a lot of libraries and applications. We usually call this block, we usually call root file system, ROOTFS. So we have mainly three blocks here: the bootloader, the kernel, and the root file system. And when we go to an Android system, things are a little bit different, right? We of course still have the bootloader because we need the bootloader to boot the Linux kernel. Of course, we still have the kernel Linux, but with some extra features. We're gonna talk a little bit about those features. And the user space of an Android system is very, very different from a Linux system. And we're gonna basically focus here in this presentation on the user space of an Android operating system. We usually call this the Android platform. And that is the source code that Google provides us in the package that they call the AOSP, Android Open Source Project. Another way to view the Android is this diagram. So I remove it from the previous diagram, the first two blocks, the hardware and the bootloader, to focus only on the operating system. So we have here basically two main components: the Linux kernel and the Android platform, the user space of the Android operating system. As we're going to talk a little bit about in the next slides, the kernel has some extra features to work with Android. But where Android is really different is in the user space. You're going to see that's really different in a lot of different aspects, like the way you manage the source code, the build system is different, the tools that are used in the system, the libraries, the daemons. Most of the daemons in an Android system doesn't have any sense on Linux, like it was really built by Google for Android. So although Google uses a lot of, I don't say if I would say a lot of open source components, but it uses some open source components, like some common libraries that we have in Linux, for example, OpenSSH or libssh. But most of the software components in Android comes from Google. Google really like build the user space from scratch for Android. And we're gonna talk about that in this presentation. I'm not go over the details right now because that's part of the presentation, right? But we can see here that we have three main layers in the user space of an Android system. We have in orange the native layer, where you have all of the libraries and daemons, all of the code that runs outside the virtual machine. We usually call them the native layer. On top of the native layer, we have the Android framework. That's what we call those red blocks. Those are the framework. Basically, all of the business logic of the Android operating system are inside this framework. We have the virtual machine, the system services, and the APIs. And on top of that, we have the Android applications. And that's usually what we, as a user or developer, see, right? The API. But there is a lot of things going on, and we're going to talk a little bit about in this presentation. So let's start with the kernel. So what's the difference between a kernel that we run in a Linux distribution or an embedded Linux distribution that we build with Yacht or Buildhood? What is the difference between the kernel that we run on Android? It's of course the same kernel, but it is a downstream kernel. It's a kernel based on the mainline kernel. And we have some features that we need to run Android. I don't have time to talk a lot about all of the features or all of the main features because I will focus here on the user space. But it's good to mention some features that we need to enable in the kernel to run Android. One of these features is the binder. Binder is the IPC, the inter-process communication, and the RPC, the remote procedure call implementation in kernel space for Android. We're going to talk a little bit about the binder, how does it work later. But for now, it's good to know that binder is the main. It's really part of the operating system. Everything that happens in Android goes via binder. All of the communication between the process goes via binder. So it's really part of the operating system. You really need binder to have an Android system working. The other piece of software that we need in the kernel for Android is HMAN. HMAN stands for Android Shared Memory. It's basically the shared memory allocator for Android. For some reasons, Google decided to not use the POSIX implementation of shared memory and decided to have his own implementation. And that's why we have HMAN. Another feature that's worth mentioning is the low memory killer. That's basically an implementation in kernel space of low memory manager. It is implemented on top of the out of memory killer, the default uh, low memory manager of the Linux kernel. And for some reasons, also Google decided to change a little bit how the out of memory killer works. For example, the out of memory killer will kill a process when the system is out of memory. Um, the out of memory killer will use some algorithm to decide which process should be killed, and will just kill the process. And that could cause problems in Android because you cannot kill any process in Android. Some processes are very important, so you you should have ways to, for example, disable the out of memory killer to kill a specific process. So the low memory killer adds some new features to the out of memory killer, some new rules that are used in Android. These are three examples of changes that were done in the kernel for Android, and there is a repository, a kernel repository that they call kernel common repository, with all of the patches to run Android. The fact is that today the mainline kernel have the needed features to run Android. So today you can download the mainline kernel and enable those features and boot an Android user space on top of it. But there are more patches than that. Usually Google uses the LTS version of the Linux kernel. So this is the image of the branching model of the Linux kernel. It's available in the Android website, source.android.com. Here we can see that Google takes mainline LTS kernel and then creates a branch for a specific Android release and develop on top of this branch. And it keeps rebasing this branch when new LTS versions are released. And yeah, there are a lot of changes that Google applies on top of the LTS versions. So if you clone the kernel common repository from Google and search for commits with the message that starts with Android, that's a standard that they created. So all of the commits that start with Android came from or were applied for Android. Uh, you're gonna see for Android 11, the last released version, we have more than 1,000 patches for Android. Not that all of those patches are required to run Android, right? Because there are a lot of patches that comes from partners, telecom providers. But yeah, we have a lot of patches. Some of them could be important or could provide some feature that a new version of Android needs to run. So usually when we are porting Android to a hardware platform, uh, usually we expect from the silicon provider a BSP with a Linux kernel with the Android patches applied. Sometimes we don't get this version with the Android patch applied. So we have to get this kernel common repo and or cherry pick the patches or rebase. We have to apply those patches to have all of the features that we need for that release of Android. So yeah, we talk a little bit about the kernel and how it differs, right? So we need some specific features in the kernel to run Android, like binary and hashman. Now let's focus on the user space, what we call here the Android platform. So the Android platform is the user space part of an Android operating system, and it is provided by the Android open source project. The Android open source project is made of hundreds of repositories. So if you download a version of Android, for example, the Android 11, uses more than 708 repositories. So the project is composed of hundreds of projects, right? And that's why they created, when I say they, I mean Google. They created the tool called repo that helps to manage this project that describes the project, right? So we have a XML file with a list of the projects, and you use this tool called repo to download or to clone those repos. So basically these two lines, repo init, repo sync, basically these two lines will download the latest version of Android. Should take a while because it's a lot of source code. So the repo init will clone a repo and do some setup, and the repo sync will go over all of the projects, describe it in a XML file, and will clone those repositories in your machine in specific directories. So in the end, after several hours, you're going to have all of the source code of Android in your machine. So Android 11, for example, the source code is around 100 gigabytes of disk. And when you do a build, it's gonna take more 100 gigs of disk. So yeah, Android uses a lot of disk space because the source code is huge. That is the listing of the source code, and here we can see one of the differences, because when you think about when you are working with an embedded Linux device, for example, we are working with a build root or Yocto, we don't have this structure of the project, right? Because here we have all of the source code of all of the user space. Everything is here. That's why it's 100 gigabytes of disk. Um, and that's not common, right? It's like a big, huge application. And that's, of course, that's not how it works, because we have here more than 700 repositories with source code from different projects. But the final view that we have is that a really huge application that you build with Make. And we're going to talk a little bit about the build system. So we have everything here, all of the software components to build the images for an Android system. Everything is here organized in those repositories. I usually say that the Android open source project is open and somewhat also closed, because from the perspective of the community, is open because you have access to the developers and the community. We have discussion groups, and then we can use those discussion groups to talk to people, talk to developers. We can contribute to the project. So Google developed this tool called Garrett. It's a kind of code review tool. We can submit patches using this tool. Those patches are going to be reviewed from someone, and we can fix bugs in Android or maybe add a new feature. So from this perspective, the Android is an open source project, right? But when you think about it, the development of the operating system is closed, because, for example, Google for sure is developing already the Android 12, but we don't know what's happening, what's being developed. We can contribute to Android 12 until they release the source code next year. So the development of the project is happening at closed doors. We don't know what's happening until they open the source code. So from that perspective, it's a closed project, right? They open and release the source code when they feel they can do it. And that, of course, differs from an embedded Linux device where you have all of the source code and you can contribute with any project, right? Also, there are some differences in licensing. Google doesn't like GPL and its variations. So we're going to talk a little bit here and give some examples. So the vast majority of software components in Android are permissive, uses permissive licenses like Apache, BSD. There are some GPL licenses, yes, but very small compared to Apache and BSD. And of course, there are closed components in Android, especially the Google applications, right? All of the applications are closed. You don't have the source code. If you want to add to your device, for example, Google Play, Google Maps, you have to certify your device, and there is a process for that to to be able to say that your device is an Android powered device. Let's talk a little bit about the build system. So yeah, we have today Yocto embedded build hood. So Android uses one of those two build systems. No, Android has his own build system. In the past, the build system was basically based on makefiles. Android, so you had hundreds and hundreds of Android.MK files in the source code. But during the development of Android, they start having some shortcomings. For example, the time to build Android starts to increase. They start to have some problems debugging the build system. So they decided to replace with a build system that they call it SOONG. So this build system is different from we are used to, right? So in build hood, we basically have a build system that is based on make files and a make tool. In Yocto embedded, we have a build system that are based on recipes, and we have the bitbake tool to process those recipes and other metadata. In Android is very different. So right now we still have some make files in Android, but they are moving the make files to another file called blueprint file. So we have a lot of Android.bp files in the Android source code. It's a file with a JSON syntax. The idea of these files is to make it possible for you to define how a software component would be compiled. So how would you like this library to be compiled? This application could be a Java application, a C++ application. So you describe how the software will be processed using those files, right? Just like you take a bitbake recipe and describe there how that software component will be processed with that recipe. That's the same thing, but with another language. That's the blueprint language. And you have the blueprint tool that will process those blueprint files to produce another file called Ninja. And then the Ninja file will be processed by a tool called Ninja that will generate the software components that will really do the build. Of course, they didn't move all of the make files to blueprint files, so it's kind of a transition yet. So to still keep supporting the make files, they created a tool called Katy or Katie. I don't know how to say. I think it's Katy, but so this tool will take the make file and then convert to Ninja files, just like the blueprint tool take the blueprint file and convert to Ninja file. I have here just to show you what is like this file. So this is Android.mk file. It's really simple, right? You describe the source code in a variable called local source files. You describe the name of the module that you want to generate in a variable called the local module. And then you say what you want to do in the end of the file with a macro. Here it calls build executable. So here we are saying to the Android build system, take this hello world.c and build it and generate a hello world binary with it. And if we use a Java file there, it's going to use a different tool. So based on the file extension, it will know what the build system will do with that, right? And of course, the build type also makes a difference here. So yeah, it's very simple if we think about it. Of course, there are more complex examples, but the idea is to describe how to build software, right, with those files. And that's the same here. So, but here we have a blueprint file. It's more simpler than the make file, I think. I really prefer this version. So you describe what you want. I want to build a binary, and then inside you describe the parameters to build that binary. What would be the name of the binary? Where are the source code? If you want to link to other libraries, you have to say here. And yeah, it's again simple to write, and there are documentations to write those files. So in the end, that's basically how the build system works, right? We have basically two tools: the blueprint tools that will take the blueprint files and generate Ninja files. We have the cat tool that will take the ANDROID.MK files and generate Ninja files, and the Ninja files will be integrated in a file Ninja file that will be processed by the Ninja tool that will create the binaries. Very different, like if we compare to build system like BuildRoot or Yocto Open Embedded. In the end, we have the image. And building Android is basically what we have in this slide. We search a script that will set up the environment of the terminal. Then we have available some tools. One of these tools is the launch tool. You select what they call a product with the launch tool. It's a kind of, when you are working with Yocto, you have to set up the machine, right? And the distro. When you are working with BuildRoot, you can load the dev config that describes what for which board you are trying to build that Linux system. And for Android, you use the command launch to configure the terminal with the variables that will define for which product you want to build Android. Then you run by make, then you wait several hours. In the end, you have images. And yeah, that is usually when we work with an embedded Linux system, we have 3-4 images at most, right? We can have the bootloader, the kernel with device trees, and then the root file system. In Android, we have a lot of different images. We have, I'm going to talk a little bit about it, but we have the system, product, vendor, OEM, user data, cache, and every image has its purpose. Organization of the root file system. There is a kind of standard, right? When you go to Debian, Fedora, you could see some differences, but the organization of the root file systems is pretty much standard. You have on all of those Linux distributions, you're going to have the bin directory, the sbin directory, the user directory, the lib directory, and everything. And that's good, right? We have a standard. So Android follows that standard, right? No. Android doesn't follow that standard. So if you list the root file system of an Android system, you're not going to find an sbin directory, an user directory, a lib directory in the root file system. Of course, we have the lib directory, but it is inside the system directory. So we have this /system/lib, but not /lib. So it's different, right? The root file system differs from a typical embedded or Linux system. And if we look at the partition layout, we have a lot of partitions in Android. Here I have 2 slides because from Android 10 on, it's a little bit different. They are not using the run disk as the root file system. So until Android 9, we have a run disk that will be mounted as the root file system, and inside there we're going to have init scripts that will mount the other partitions. In Android 10, and now 11, we still have the hand disk because it's necessary. So the system partition can be checked with the envarity, but the run disk is not the root file system anymore. And why do we have all of those partitions? Because Google is worried about the changes in the base operating system. So the system partition would be the base operating system, what comes from Google. But we have other players in Android, right? We have the silicon provider, for example, Qualcomm. We have the device manufacturer, for example, Samsung. We have the telecom provider, for example, AT&T. All of those players would want to do changes in the operating system. So we have the system partition to Google, we have the vendor partition for the silicon provider, we have the ODM partition for the device manufacturer, and we have the product partition for the telecom provider. So every player could do his own changes in his own partition to not mess up with other partitions. And that would, in theory, improve, for example, the ability to update the system. So that's why we have a lot of partitions in Android. Another thing that Android differs from an embedded Linux system is the connection with the device, right? So usually on an embedded Linux system, we have serial connection with the device, but if we take an Android device, especially a mobile device or a consumer device running Android, we don't have visible, accessible serial port. So Google tried to solve that problem with a tool called ADB. So that's a tool that was created specifically to run on Android, although we have ports to run on Linux. The ADB tool is composed of several components. We have the tool that you run in your development machine. So you run ADB in your development machine. It will talk to a server in your machine because the idea of the server is to make it possible to communicate, to have a lot of clients communicate with the same device. And then on the target, you have a gadget driver that will receive the packages, right, from your host machine and pass those to the daemon that is running in Android that will execute the commands that you're asking. So you can do a lot of things with ADB. We can list the devices with ADB devices. You can pull or push files, so you don't need SSH in Android. You can use ADB to transfer files between the target machine and the host machine. You can open a shell. If you run ADB shell, you can open a shell and have access to your device. If you are running a development build, they call it eng build, you have root access and then you can do everything you want in the device. But of course, if you try to do an ADB shell to a mobile device, you won't have root access. You have shell access and not much can be done there. Very nice. So far we talked a lot about the source code, how it differs, the build system. Let's talk a little bit now about the native layer. The native layer, we call it native because it's running outside the Java virtual machine, so mostly code written in C++. Let's talk about some difference that we have in the native layer of Android compared to a Linux system. First, difference is the C library. So the C library is our API to the kernel, right? We have a lot of C libraries in Linux, glibc, uclibc, musl. So Android must use one of those C libraries, right? Of course not. Android uses his own C library, and it's called BIONIC. I can see 3 reasons why Google decided to use the C library, the BIONIC as a C library. License, speed, and size. Google doesn't like GPL, right? And glibc and uclibc are both GPL. Maybe Google could use musl, but I think maybe at that time, 10 years ago, musl was not ready yet for production. So maybe that was the reason they didn't. They decided to not use musl, and they decided to create or maintain his own C library. That as far as I remember, it was based on a BSD C library. The only thing about the BIONIC is that it's not really POSIX compliant. So if you try to build a Linux application on Android, you could have problems. Just an example, this is a snippet of source code from BusyBox, the last version of BusyBox. If you grep for Android there, you're gonna find some if that's inside the source code. So if that Android do this and not that, because there are some like some missing APIs in Android or some differences in the behavior of some APIs in the BIONIC. So we have to adapt our software to the BIONIC library. Another difference that we can see in Android that we don't see in Linux, in embedded Linux system, is BusyBox. So BusyBox is a very common tool, right? Almost every embedded Linux device has BusyBox installed. BusyBox provides a lot of common tools for an embedded Linux device, but Android doesn't use it. Probably because it's GPL. So Google started developing his own version of BusyBox called TOOLBOX. Then after a while, they decided to develop his own. They decided to adapt a community implementation called TOYBOX. That's developed by Robert Landley. That was one of the maintainers of BusyBox, but he's not anymore. The fact is that BusyBox has a lot of tools. So this is a listing of the BusyBox tools. And if we take the listing of the TOOLBOX and the TOYBOX, like it's kind of a half of what we have in BusyBox. So usually when I'm working with an embedded Android device, I usually install BusyBox in the device. Because for example, if you want to run VI in the device, you will need BusyBox because you don't have VI in TOOLBOX or TOYBOX. So yeah, VI is just an example, but yeah, there are a lot of tools that the BusyBox provides that these two tools doesn't provide. And yeah, it's just a matter of changing the build system, right, to include BusyBox, to build and include BusyBox in the image, but you have to do it because it is not available by default. Init system. So init system is another part of Android that is very different. So you would expect that Android would use a common init system like System 5 init or System D. No, Android has its own init system. And it's very different in a lot of different ways. So yeah, it's an init system. So it will do the startup of the system. It will start and manage the daemons. It will do some other things like manage system properties. But the way you configure, it's different. It's not like that you set up some shell scripts and you're done. No, it had its own syntax. So in the boot, the init demo will read some init scripts. Those are files with RC extension, and then we'll process those init scripts. And they are very different. They have like declarations of actions. For example, here we have on early init. So when this action happens, when this action is triggered, you have to execute these commands. Here I have more examples. When this action is triggered, you have to execute those commands. And you can see those commands are not shell commands, are init specific commands. So you don't have a symlink command in the shell, right? If you want to create a symlink in the shell, you're gonna run ln something. So you have actions and commands. And during the boot, the init process will trigger those actions and will run those commands inside those actions. We have also declarations of services. It's like daemons. When you declare a service, it doesn't mean that the service will run, but it means that this service exists. To run the service, you're going to have to use the start command, for example. So we start eventd, we'll run this daemon with these options. So yeah, we could have a whole presentation all focused on this, but yeah, we don't have time here to talk about it, but I just want to mention that's very different. Another thing that is different in the Android is the shell. It's very, well, shell is the shell, right? But if you, for example, try to run a shell script that you run in Ubuntu, for example, or Debian, if you try to run in Android, you could have problems because it's not, you're not running the born again shell or any other shell implementation in Android. You're running the mere BSD shell. That's a more limited shell implementation. We have also a lot of daemons in Android, those processes that run in the background doing something. But if we take a look at the daemons in Android, we're gonna see that they are very different. So most of the daemons in Android, we don't have in Linux. The Android basically like have implementation of a lot of daemons that we usually have in Linux. For example, in Linux, you have the udev daemon to manage hot plugging of devices. In Android, do we use udev? No, we have another daemon called uventd. We have a daemon to manage storage devices, the VOD daemon. We have a daemon to manage communication with the radio, the Rio daemon. We have a daemon to manage the networking, so we don't use a network manager or command in Android. We have a specific daemon for that, netd. All of those daemons were developed by Google. So if we list the process running on an Android system, we're going to see a lot of different daemons that we don't even know about it because it's really specific to Android. That's the same with logging, right? We have a specific log with Android. Android doesn't use syslog or journal control for logging. It has a specific daemon called logd to do the logs. And this is the output of the log in Android. You just run logcat and you have everything that. And I really feel that the logging system in Android is very well done. And to finish this native layer, it's good to talk about the native layer. So in Linux, if we think about it, we don't have any extra abstraction usually to talk to the hardware, right? So we have the hardware, we have drivers in the Linux kernel, the export interface, /c/dev. We could have some library on top of it, and then the applications use those libraries. On Android is very different. So this diagram is very important to understand Android in this presentation. So let's say, for example, you want to talk to a serial port. On an embedded Linux system, you have the /dev/tty. You can open this file and talk to this file. On Android, it's very different. So imagine an Android app wants to talk to this device. You're going to have to talk to an API. So you have to talk to use an API. That API is going to send a message to a service running inside the Android framework. That's going to talk to a hardware abstraction layer for the serial port. That's going to talk to the hardware. So every layer here has its responsibility, right? The API, the responsibility of the API is to provide an abstraction for the application, the functions to access the device. The responsibility of the service is to make it sure that the application can access that device, so it checks permission. It will manage concurrency to access the device because all of the access to that device will go over this service. And the last layer will provide an abstraction to the hardware. So if you change the kernel interface, you change the abstraction here, and then the service will keep running. So yeah, in Android, it's very different in this sense, right? Because we have a lot of layers, and of course, an application here could access directly the device, but you would bypass all of the rules that Android and Google defines, the permission, the security, the abstraction, and everything else. So if you want to support a device in Android, you would have to develop, if you want to follow the standard, right, you have to develop a HAL for the device, a service for the device, and possibly an API for the device. And yeah, it's very different, right? All of the communication in Android occurs via binder. So binder is the implementation in kernel space for communication between processes. So we have one process wanting to talk to another process. In our case here, we have the service that wants to talk to the HAL. So here it's going to exchange messages, and then it's going to use binder to exchange those messages. We are finishing the presentation, so let's talk a little bit about the framework, and then we can finish the presentation. In the framework, that's where we really have the business logic of Android. The system service has all the logic, to access the resources provided by the operating system. So we could have hardware resources or system resources. For example, sensor is a resource, power is a resource, battery is a resource, camera is a resource. Every resource has a service in the framework. Inside here, the system service. The service provides an API. It provides a remote access, so interface that you can talk to, that you can consume. And the APIs will talk to those services to use those services. We have in Android 11 184 services. It's a lot of services, and most of those services. So again, that diagram, right? An Android app, for example, wants to talk to a sensor. Is going to call a sensor API. That's going to send a message to a sensor service. That's going to abstract the access, centralizes, manages concurrency, and then checks permission. After that, it's going to call a HAL. That's going to abstract the access to the hardware, right? That's how Android works. And if we think about it, it's very different from a Linux system. What is nice about Android that you have a lot of tools in the command line that we can use. For example, if you want to do a call in the command line, you can just call the service with the right parameters. So here I'm using the service call command with the right parameters to do a call to a specific number. Very nice. So this command will send messages to the service. And of course, here I'm running as root. That's why I can do it. And we have, of course, the application on top of everything. And if we compare to a Linux system, the applications are very different, right? By default, we develop applications in Java or Kotlin. Of course, we could use other tools with bindings for other languages, but by default, Java or Kotlin are both the default languages for Android. And they are packaged with a file format called APK with the codes, resources, and everything else, and we install it. We could install it using a marketplace, the Google Play, or manually if we want. The applications in Android are composed of different components. I don't have time to go over those components, but yeah, it's a little bit different from Linux graphical application, for example, using GTK or Qt. And the applications communicate over protocol that Google created called intent. I will talk a little bit about fragmentation, but unfortunately, I don't have time to talk about it, but Google worries a lot about fragmentation, especially because they want to update frequently Android, but they can't because from the released source code to the final version of Android released to the user, we have a lot of changes made by the silicon provider, and that's a problem. So they created projects like Treble, Project Mainline, the kernel, the full image that they created. A lot of projects to try to improve the situation. That's why sometimes the architecture of the operating system is a little bit complex, right? Because they are trying to solve this kind of complex problems. So to conclude my presentation, I would say, what is the similarity between an Android system and a Linux system, the Linux kernel? Almost everything else is different. It's different, right? From the way you manage the source code, the way you build the components of the source code, the distribution, right? The daemons, the command line tools, the libraries, the way the components communicate using binder. So almost everything else is different. So should we say that Android is a Linux distribution? I would not say that. I will basically say that Android is an operating system based on the Linux kernel. Very nice. Some final references if you want to check out. Basically, the main documentation is source.android.com. You can have a look at the source code, right? And of course, there are some good presentations from Karim on YouTube if you want to check out. That I would say are the main references to study and follow Android. I hope you guys enjoyed this presentation. Those are my contacts. Now I'm gonna open this session for question and answers if you have time. And thank you all for your time. See you in the next talk. Bye bye.